Okay, hi guys. So in this lecture we'll be continuing on seeing the nucleophicity order in polar protic solvents. So we deal with the case 3 where we have all these compounds in polar aprotic solvent. So let it be water in this case. So as you can see, the charge on negative the stability order would be something like this, but as the atom size is smaller, it would be having more hydration energy or more hydration with the OH molecules, O minus H molecules of the rather this thing. Okay, so due to which it gets surrounded by water molecules, so its nucleophicity would decrease. Hence, the nucleophicity order would be something like this because of its bulky size. And similarly, we can see that as in this case also, if we have something like this, this would be the nucleophicity order, and same in this case as well. Okay, so the important thing to note here is the more hydration, less nucleophicity. So more hydration, less nucleophicity. Okay, so now let us move on to the case 4, wherein we have that nucleophile with lone pair on adjacent atoms is better. Okay, so case 4 is that nucleophile with lone pair on adjacent atoms is better. Okay, what do I mean by this? We have something like this, wherein so here this is a better nucleophile with just one oxygen atom. Okay, why? Because on the adjacent atom we have more electron density here, so this can donate more freely. Okay, so just a qualitative measure to understand the principles, or better remember the principles. So here we have only one pair, and here we also have one pair, but better electron density on the adjacent atom relaxes this atom to donate even more. Okay, so this is the order of nucleophicity. So now let's discuss the nucleophicity in polar aprotic solvents. So nucleophicity in polar aprotic solvents. Okay, so in polar aprotic solvents, for instance, we have this. So due to the bulky nature of these two CH3, we have to keep in mind the two bulky nature of this CH3, and we need to compare the nucleophicity of these compounds. Okay, so the order would be something like this. Because as the size of the atom gets smaller, so it would have more space to attack to the electrophile rather than this, which will also be having more steric repulsion with respect to the two CH3s attached on this aprotic solvent. Okay, Or another way to look at this is, this oxygen is having a delta negative charge, and if it's surrounded by F minus all around the place, they are going to have more repulsion, as both are means as F is more electronegative than O. Okay, and F is indeed the most electronegative element in the periodic table. Hence, O and F would be having the most repulsion, due to which F would readily go and attack on the electrophile. Okay, and I, as minus charge on I is more stable, hence these O and I will be having relatively less repulsion than O and F. Hence, it would be a poor nucleophile, and the order would be in decreasing order. Okay, similarly, on the same principle, we can say that OH is actually a better nucleophile than CS3 minus. Why? Because O and O, between this O and this O, they will be having more repulsion because of the smaller size of O and relatively same electronegativity than the O and CS3. So due to the repulsion between OH and SO, it should be delta SO, it would be more showing the nucleophicity. Okay, so but the order was actually just the reverse in polar protic solvents. Okay, because of the hydration. So as we talk about the polar protic solvent, why this is the case? Because OH minus would be more hydrated. What I mean by hydrated is surrounded by the water molecules around the OH minus. Okay, we'll be looking into the more of the hydration energy concept in our inorganic lectures, but for now you can safely assume them that by hydration I mean more surrounding of the water molecules across this reagent. Okay, so let us talk about the steric hindrance in nucleophicity. Okay, so more the degree of carbon, less is the nucleophicity. So more the degree of carbon, less the nucleophicity. Okay, so we have some examples like this, wherein we have to compare the nucleophicity of this and this. So obviously the third one would be the most nucleophile, having most nucleophicity. Why? Because it has not to carry these bulky groups along with itself to attack on a electrophile. Okay, so this has to carry along with only this much smaller substituent along with itself to attack on a nucleophile or on a electrophile. Okay, but if you compare the basic order would obviously, this would be more basic, but the basic strength is just the reverse. Okay, so now let us look into something like this, that primary alcohol is a better nucleophile than tertiary alcohol due to the same reason of steric hindrance in nucleophicity. So primary alcohol is better nucleophile than tertiary alcohol. Okay, so with this we end this lecture, and from the next lecture we will be seeing SN1 reaction or SN1 mechanism in nucleophilic substitution reaction. Okay, so till then, good luck and goodbye.